Yep.
Yeah.
Okay, cool.
All right, let's get it.
Hi, my name is Nathan Reinica.
I'm Alexa Gallo.
I'm Chris Mann.
I'm Luis Mendoza.
I'm Tracy Reeves.
I'm Chris Rice.
I'm Michael Vasu.
And we are Team Swamp Hopper from the University of Florida. We are here today to introduce our new light attack aircraft. Designed to replace attack helicopters such as the Apache that are commonly seen on the front lines, our aircraft is faster, safer, has more firepower, and is a more affordable option. Capable of short runway takeoffs in severe landing conditions, the aircraft possesses the capability of utilizing a string of runways, opening up deployment options. Equipped with two 50 caliber machine guns, as well as being able to carry modularly attached explosive loads of up to 3,000 pounds, the Swamp Hopper is versatile in its air-to-ground and air-to-air capabilities. To begin our design process, we looked at case studies of similar aircraft and the weight to determine the weight at takeoff. First, we started by finding aircraft of similar make and purpose in order to get a general idea of its most basic characteristics, such as weight and horsepower. Finding the average weight of the Super Tucano, AC-6 Wolverine, and the Piper Enforcer, we found an initial estimate of our aircraft's weight, which we then made more precise by using an iterative method of analysis, a section of which can be seen in the upper right-hand corner of your screen. In order to use this process, we had to have an idea of the missions that the aircraft would undertake, such as deployment and maintenance mission trips represented here, and the data regarding historical trends for fuel consumption during various legs of the trip. Finding this, we determined a weight estimation of approximately 11,000 pounds. This value being utilized during our design process until enough of the aircraft was developed to find a more accurate representation.
Next, we'll be talking about the airfoil selection and wing geometry design. 4 different airfoils from similar light attack aircraft were compared based on their coefficient of lift, coefficient of drag, moment coefficient, and angle of attack. And the NACA 63412 was chosen for multiple reasons, and this is indicated as the blue lines in the graphs. It has one of the higher lifts during stall, which can be seen in the top right graph. It has a better lift to drag ratio, which can be seen in the bottom right. And it has one of the smallest moment coefficients, which can be seen in the bottom left. Moving on to the wing geometry design, we estimated the span and total wing area of our aircraft based on the 3 similar light attack aircraft. And we found these to be 38 feet and 211 squared feet. We use these values to find the aspect ratio, which was then used to find the quarter chord sweep at subsonic flight. And this sweep allows subsonic airflow over the wing and diving maneuvers, and also provides the benefit of increasing static stability for the aircraft. The sweep was then used to calculate the taper ratio using an elliptical lift distribution. And this helps minimize any drag due to lift. A low wing design was chosen over the mid and high wing design for multiple reasons. It increases maneuverability and gives the pilots a clear overhead view, which is crucial for dogfights, and it also allows for landing gear storage. The dihedral was estimated based on existing data of similar aircraft, and since a sweep was already added, which creates a dihedral effect, we chose to use a smaller dihedral value, and this helps with lateral stability. And a cutoff wing was chosen rather than having a round wingtip because air can't easily flow around the wingtips with cutoff wings, and this helps increase lift while decreasing drag. An incidence angle of 2 degrees was selected because it maximizes the lift at takeoff, and it also minimizes the angle of attack at cruise. And finally, a twist angle was selected to prevent tip stall and also revise the elliptical distribution. And all of these values were selected to optimize the aircraft during its missions, and these values can be seen on the right-hand side in the table.
Okay, moving on to the propulsion part. We chose a turboprop engine due to its higher efficiency at low altitudes in comparison to jets. This leads to a more cost-effective design for short distances as required by the design mission. In fact, a turboprop engine guarantees the aircraft to take off and land on shorter and non-concrete runways more easily, which is crucial to provide air support to the front lines in austere fields. More in detail, we chose the Pratt & Whitney PT6A 68D engine due to its 1600 horsepower, which is approximately equivalent to 3 Corvettes. Furthermore, this engine allows for more versatility due to the extra power this one offers for the design mission, while also being a reliable option as it is commonly chosen in many other aircraft. Regarding the propeller design, we designed a 4-blade propeller with a stretched version of a NACA 4412 airfoil. As you can see in the table, based on an assumed propeller efficiency of 0.4, we calculated the required diameter as 7.167 feet for a thrust and power coefficient of 0.3347 and 0.74 respectively, to avoid the formation of a wave shock while providing enough thrust. Finally, it is important to point out that we decided to incorporate a single engine at the nose to design for a more stable aircraft while optimizing the efficiency of the propeller with cleaner air at the inlet. Regarding the fuel systems, we calculated that 1,700 liters of fuel would be needed, considering an extra 6% for reserve and trapped fuel. We figured out that 465 liters out of the 1,700 would be in the wings with bladder tanks, while the remaining fuel would be in the fuselage within rigid tanks. We chose bladder tanks in the wings due to its self-healing capacity in the case the wings get shot by the enemy.
Moving on to the landing gear, the Swamp Hopper's landing gear was arranged in a tricycle formation with one auxiliary tire in the front and 2 main tires further back. This allowed for the weight to be evenly distributed across the 3 wheels and allowed the aircraft to be more stable for takeoffs and landings. The landing gear is stored under the fuselage with a hydraulic system. When considering shock absorbers, an oleo strut was chosen. Even though they can be more complex, the ability to adjust different force responses to different loading factors is valuable. The oleo struts can be seen highlighted in red on the figures to the right. The static and dynamic load were calculated to find the diameter and width of the tires for the landing gear. The calculations considered weight distribution between the auxiliary and main wheels to ensure no failure. A 7% margin of safety was also added to these calculations. The maximum static load for the auxiliary tires was calculated to be 1,703.7 pounds, while for the main tires it was 5,307.5 pounds. The minimum static load for the auxiliary tires was 908.6 pounds, and the braking load for the auxiliary tires was 1,723.3 pounds. The total kinetic energy of 5,067,700 Newton meters per second was then determined to calculate an approximate tire diameter. Based off the results from the static and dynamic load calculations, the tires were selected for both types of wheels. The calculated tire characteristics from the static and dynamic loads were then increased by 30% to ensure that the aircraft could operate on rough, unpaved runways. The tire selected for the auxiliary tire was a Type 7 aircraft rib 18 by 4.4 inch tire, while the main tires were selected to be a Type 7 Flight Leader DT 26 by 6.6 inch tire. The weight distribution between the auxiliary and main tires is 10% and 90% respectively. Other major factors considered in the selection was the rated pressure and load. The applied pressure and load of both the tires selected had to be lower than the rated pressure and load to ensure that the tires would not fail.
The next design focuses on the crew station and the fuselage. To find the best ratio of available internal volume to total length of the aircraft, a fineness ratio of 8 was used as it is optimal for a subsonic aircraft. The initial length was estimated using the gross takeoff weight, and the value was used to determine the average diameter of the fuselage. Once the sizing was completed, geometry was implemented with added focus on maintaining smooth contours to both reduce drag and radar signature. The propeller acts when considering detectability, the turboprop design offers an advantage compared to a jet aircraft. The propeller acts to mix the free stream air with the engine exhaust and effectively makes the engine heat signature, masks the heat signature with the surrounding air. Other countermeasures it also is equipped with include ECM jammers as well as chaff flares. The crew station is built to seat 2, and each crewman has a 0-0 ejection seat in case of an emergency during flight. Canopy and cockpit geometry is optimized to comfortably fit both crewmen and offer superior visibility. The low-mounted wing helps accomplish this, and either pilot has to struggle to look over the wing. When it comes to safety, firewalls are installed around the crew at higher risk areas, including near the engine and the fuselage fuel tank. The Swamp Hopper is equipped with primarily air-to-ground weapons package designed to engage ground targets. This includes Mark 82 unguided bombs, GBU-12 Pathway 2 guided bombs, and AGM-25 guided missiles. Each of these are launched with the rail mechanism. Additionally, 50 cal machine guns are mounted on top of each wing so that the net recoil they produce is 0, and they will not affect flight performance. The guns are mounted far enough away from the fuselage to have clearance of the propeller, and the smoke generated by fire will not reach the engine intake. The combined weight of the armament exceeds the 3,000 pounds required by the RFP, and this package can be easily optimized for different missions due to the external mounting configuration.
Next, we're going to be talking about the structure part of the Swamp Hopper aircraft. The first task for the structure section was to create a VN diagram. To determine the aircraft limiting performance, a VN diagram is used to illustrate the variation in load factor as a function of the equivalent airspeed of the aircraft for different maneuvers. The aircraft load factor indicates the maneuvering of an aircraft as a multiple of the standard acceleration due to gravity. The equivalent airspeed is defined as a direct proportionality between the speed of the aircraft relative to air and the square root of the density ratio, which is described as the density normalized by the density at sea level. When looking at the figure on the right, the first line on the left-hand side that curves up is the maximum lift line. This then stops at the high angle of attack line, which is then connected to the vertical line on the right. This vertical line on the right is the maximum dynamic pressure line, also known as the Q limit line. Finally, the lines below the x-axis are created from the different velocities. First, the line on the left-hand side that curves down going up until the V cruise is created from the V stall line. It stops at the V cruise line, which we can estimate for our aircraft to be roughly 110 meters per second as seen in the figure. Then the line on the right-hand side that slopes back up and connects to the maximum Q line is the V stall line. Next, the fuselage and wing structure types needed to be selected. For the fuselage, the 3 structure types that were researched were the truss, monocoque, and semi-monocoque structures. A truss structure uses vertical and horizontal struts that are welded to longerons to yield a square profile. The monocoque structure uses stressed skin to support all of the loads. And finally, the semi-monocoque structure involves using stringers, formers, and skin, as seen in the image below. The semi-monocoque structure was chosen as the stringers take some of the bending stress away, therefore creating a barrier for further crack propagation, and the fact that many structural members are present leads to an increased strength and rigidity. After this, the wing structure type needed to be chosen, and the 3 types that were researched were the monospar, multi-spar, and the box beam. Monospar designs only incorporate one main spar or structure member in the spanwise direction, with ribs or bulkheads providing the necessary contour of the airfoil. The multi-spar design essentially incorporates more than one spar or structural member along the spanwise direction of the wing. And finally, the box beam design uses 2 main longitudinal members with connecting bulkheads for additional strength and to give more contour to the wing. By examining similar aircraft such as the Super Tucano and examining the previous design choices made for the locations of the landing gear and mounted guns, it was determined that a multi-spar design was best suited for the wing construction type. After determining the structure type, the material needed to be selected for the Swamp Hopper. The material that was selected was aluminum 2024 T42, and it was chosen due to its adequate yield stress and good fatigue stress resistance. The material's high fatigue resistance paired with the high strength to weight ratio makes it an excellent choice for wing and fuselage constructions of modern aircrafts. Some material properties of aluminum 2024 T42 are that it has a density of 0.1 pounds per inch cubed, an ultimate tensile strength of 57.3 KSI, and a yield strength of 37.7 KSI. The figure on the right shows the SN diagram for the selected material. In addition to using aluminum 2024 T42 for the majority of the Swamp Hopper aircraft, it is important to note that a titanium tub will be incorporated to the cockpit of the aircraft in order to protect the pilot from any shrapnel that may appear during combat. After choosing the structure types for both the wing and fuselage, a model of the deformed wing box geometry was created in a program called ANSYS to perform structural analysis. In ANSYS, the load were then applied with a safety factor of 1.5. From the ANSYS program, it was determined that there was a maximum von Mises stress of 30.8 KSI. After this, we went on to calculate the von Mises stress from principal stresses and calculated that value to be 25.2 KSI. Both of these stresses are below the yield strength of 37.7 KSI, so we know that our design is safe from failure. With these stresses determined, it was then found that the Swamp Hopper aircraft was rated for 10 million cycles.
Next up, we'll talk about the tail design, systems, weight, and CG estimation. So we chose a conventional tail design configuration because of its simplicity and stability and controls capabilities. After the tail configuration was chosen, we had to calculate the tail arm and position of the tail with respect to the wing aerodynamic center. This was done by using the tail volume coefficients for both the horizontal and vertical tails as seen in the first row of the table. And these values were determined for typical fighter aircraft. The calculated tail arm was then used to find the height of the tail, which was chosen to be in line with the wing aerodynamic center. And this value was within the acceptable bounds for a subsonic aircraft for deep stall considerations. Spin recovery was also considered, as more than a third of the rudder was designed to be out of the horizontal tail wake region, as you can see in the figure to the left. Other values such as the aspect ratio, taper ratio, and sweep angle were chosen to be in the range typically used for a fighter aircraft. A symmetric airfoil was chosen in order to have no lift at a zero angle of attack. And finally, with all of these design factors combined, the horizontal and vertical tail areas could then be calculated, as you can see in the bottom row of the table. The rudder and elevator, as seen in the figure, were approximated using 30% of the chord of the vertical and horizontal tails respectively. All control surfaces were tapered and cored by the same ratio as the horizontal and vertical tails, so that a constant percent of chord was maintained. In addition, both rudder and elevator were designed to be 50% of the span of the horizontal and vertical tail. A fly-by-wire control system was chosen as the primary control system. The fly-by-wire control system uses computers to allow inputs to be made by the pilot. This computer analyzes the inputs and moves the control surfaces accordingly to maximize the overall performance. Slotted Fowler flaps were used for the secondary control system. By using the slotted Fowler flaps, the length of the chord and angle of attack during takeoff were both increased, making it easier and more achievable to reach the landing distance requirement. For this design, the team decided to incorporate a full authority digital engine control system. This was chosen because it is a single control that combines the throttle, prop, and mixture controls all into one. Some benefits include better fuel economy, automatic engine monitoring, and diagnostic processes that will alert the pilot of any minor problem detected. Excuse me. There are 5 different subsystems which contributed to the overall performance of the aircraft. For the hydraulic fluid, an Aeroshell 31 synthetic hydrocarbon-based fluid was chosen due to its high boiling point, low freezing point, low viscosity, and corrosion resistance properties. Considering the design mission of the Swamp Hopper, a turboprop generator was chosen, which would provide a typical 28-volt direct current to the system, and in which a nickel-cadmium battery would be needed to start the airplane. A pneumatic system was used to provide compressed air for pressurization, anti-icing, engine starting, and environmental control. A jet fuel auxiliary power unit was chosen since it was designed to produce ground power for the engine, starting the air conditioning and cabin lighting. Different avionic devices, such as an electronic countermeasure device and infrared jammer, were chosen to ensure the satisfaction of mission requirements for a military aircraft. Other systems, such as the fuel tanks, landing gear, and control surfaces, can also be seen in the figure as well. So the moment created by each component had to be calculated, and this was done by multiplying the weight of the component, as seen in the second column of the table, by the location of the component's center of gravity. And the center of gravity of each component can be seen in the figure to the left, which is color-coded to match the colors in the table for each component. The total weight estimation for the Swamp Hopper was then determined by adding all of the main component weights of the aircraft, which gave an overall total weight of 10,830 pounds. The center of gravity was calculated by adding the component moments seen in the previous slide and dividing that total sum by the total weight. This gave a calculated center of gravity of 11.01 feet, measured from the nose of the aircraft as seen in the figure. The z-direction center of gravity as measured from the bottom of the deployed gear was found to be 4.912 feet. The center of gravity envelope during the first mission was found by taking into account the weight of the fuel consumed in the first mission during the center of gravity calculations described previously. By doing so, the center of gravity of the aircraft at each leg of the mission was calculated and plotted against the weight of the aircraft, normalized by the starting takeoff weight. It was found that only a small change in the center of gravity occurred between takeoff and the loiter, as seen in the figure in the bottom right. Next, we'll be talking about the stability and control of the aircraft. For longitudinal static stability, two different requirements had to be met. The first requirement was a trim condition. For trim conditions to be met, the pitching moment coefficient about the center of gravity, also known as CMCG, had to be approximately equal to 0. For longitudinal static stability to be met, the pitching moment derivative, Cm alpha, had to be less than 0. The major contributions to trim and pitching moment derivative were the wing flaps, fuselage, horizontal tail, and engine, with the wing having the most destabilizing contribution and horizontal tail having the most stabilizing contribution. As you can see in the table, both trim and longitudinal static stability conditions were met as CMCG at takeoff and landing was approximately equal to negative 0.044, which was smaller than the 0.05 magnitude that can be corrected with the elevator deflection. Also, as you can see, Cm alpha was less than 0 and within the acceptable range for fighter aircraft. In addition, the neutral point, which is independent of CG, was calculated. The non-dimensional neutral point was found to be 2.05, which was greater than the non-dimensionalized center of gravity value, xCG, which was found to be 1.935. Solving for the static margin yielded a positive static margin value of 0.119, which indicated that the aircraft was stable. The static margin, which is approximately 11.9%, corresponded to a more stable aircraft than earlier fighter aircraft, which usually had a static margin of approximately 5%.
Looking at the lateral directional stability of the aircraft in regard to the roll moment, it was found that the wing sweep and the dihedral angle of the wings corrected the destabilizing moment generated by the low placement of the wing, ensuring an acceptable roll moment. Furthermore, with respect to the yaw moment, it was determined that the area of the vertical tail was adequate to ensure a favorable moment. These moments were found to be negative 0.138 and 0.138 respectively, with both meeting the design requirements for developing a stabilizing aircraft. A stabilizing aircraft is one that, after perturbation, tends to return to a state of equilibrium, meaning the nose of the aircraft will return to the flow of the incoming air, becoming parallel to the velocity vector of the aircraft. This is desirable for a pilot as it means a smoother flight that is more easily controlled. In the middle figure, you can see the effect of dihedral angle on the roll moment, and how, as the dihedral angle increases, the stabilizing effect increases as well. In the right figure, you can see the effect of the vertical tail and how, as the area increases, it has a positive effect on the yaw moment. And you can look at the figure on the left, and you can see what axes the yaw moment, the pitch moment, and the roll moment correspond to.
Next, we're going to be discussing the performance analysis of the Swamp Hopper aircraft. The first part of the performance analysis was the range and endurance analysis. After performing the range analysis, which was split up into 3 different segments, the first cruise, second cruise, and loiter, it was determined that the first cruise segment and the second cruise segment both had a range of 1,307 miles, while the loiter segment had a range of 273 miles. These 3 can be totaled up for our total range to be 2,887 miles. After this, the endurance analysis was performed, and it was determined that the total endurance of the Swamp Hopper was 6.05 hours, and in that time, 1,095 pounds of fuel would be used. The tables below show the initial and final weights of the aircraft at different segments of the flight, and these were used in the final calculations for estimating both range and endurance.
For takeoff performance, the main design requirement was that the total horizontal takeoff distance had to be less than or equal to 4,000 feet, given a 50-foot obstacle at the end of the runway. To begin, our calculated stall velocity of 151 feet per second was used to estimate the ground to roll velocity, the transition to climb velocity, the climb velocity, and takeoff acceleration. Using the geometry in the figure on the left, we were able to calculate the climbing angle and the transition to climb altitude. These values were then used to calculate the horizontal ground roll distance, transition to climb distance, and climb distance. All of these totaled to be 2,757 feet, which is less than the design requirement. Similarly, for landing performance, we had to meet the same design requirement of less than or equal to 4,000 feet. And the approach velocity was used to estimate the touchdown velocity. And using the geometry on the left, we were able to calculate the approach angle and the flare height. These were then used to calculate the horizontal approaching distance, the flare distance, free roll distance, and braking distance. The total horizontal distance was found to be 3,150 feet, which is also less than the design requirement.
Moving on to cost estimation, the research, development, testing, and evaluation costs, also known as RDT&E costs, were calculated per unit aircraft. The development and procurement costs of aircraft model, also known as DAPCA, was used to estimate the cost of 50 aircraft in 5 years. From that, a unit price was found for the RDT&E costs per aircraft. Many variables are considered in the calculation, but the main contributing factors include engineering, tooling, manufacturing, and quality control costs. The RDT&E cost per unit was $11.1 million. The flyaway costs were also calculated using the DAPCA model. The unit price of the flyaway costs per aircraft was also determined by the estimation costs based of the 50 aircraft in 5 years. Major contributing factors in the flyaway cost calculation includes development support, flight testing, manufacturing materials, and engine production. The flyaway cost per unit came out to be $3.12 million. The DAPCA model was then used to calculate the RDT&E and flyaway costs for various quantity of aircraft over 5 years. From the table, a trend of decreasing amount per unit can be seen as the quantity of aircraft is increased. In the empty weight versus cost per unit graph, by using the positive linear trend with similar aircraft cost per pound, a similar price of the aircraft can be found. The operational cost for 1,200 flight hours per year was also calculated for the Swamp Hopper. Major factors contributing to the total cost for 1,200 flight hours per year were the operations and maintenance, tires, brake systems, oil, and insurance. The operations and maintenance factor can also be broken down into 3 majorly contributing factors, which include fuel maintenance, crew salaries, and other maintenance. The total cost for the 1,200 flight hours per year was determined to be $2.47 million. Thank you for coming to our presentation of the Swamp Hopper. We would love to answer any questions anyone has at this time.
Thank you so much for your presentation. I really like it. Great job. Any questions from the audience? Okay, I think he's not here. Overall, really amazing job. And they are, I think I really like the slides and also the presentation itself. It's very clear and easy for me to follow. Well, for the audience, everybody else to follow. Just a very small point that you may consider that changing in your final report, or it's just for this presentation. I'm not quite sure. So the first one is, okay, that is the, I think it's just purely for this slide and the presentation itself. I see that on page 5, this aircraft characteristics comparison. So I would consider you probably want to put the initial estimation results here, because I'm kind of feel that, well, there is a weight equation here and everything. And my feeling is that, well, we do this comparison and everything is for our initial estimation, right? We want to estimate what is the initial weight, initial wing loading, initial thrust weight ratio, lift drag ratio, everything. And then we use that one as a guidance for our later design, like design wing, design the tail, engine, everything. So it'd be nicer if you can include the information like the initial estimation results, weight, thrust weight ratio, wing loading, lift drag ratio, things like that to list here. And then we talk about the design one by one. So that is just my small suggestion for this presentation. And then now let's move on to the airfoil selection. And for the wing geometry design, is page 8. Yes, so ensure subsonic airflow during the dive and I checked your VN diagram. So the dive speed on the VN diagram is approximately Mach 0.5, right? So I would consider for your design, probably this one is not that necessary because, right, that's what I feel, because no matter what airfoil you use, it will be lower than the current Mach number of the airfoil. So for the sweep, probably you can consider is to increase static stability, but it's not to ensure subsonic airflow during the dive, because based on your dive speed, it will not have the, it's not a problem anyway. So that is the first one. And a second one is the instant angle. You put it here to maximize the takeoff lift, minimize cruise angle attack. I'm not sure my understanding is correct or not, just my personal opinion. I feel that the instant angle is to minimize the drag caused by the fuselage during the cruise most of the time. So we want to design a wing, angle between the wing and the fuselage there's a twist angle, or instant angle, sorry. And then to make sure that, well, because aircraft most of the time spend the time in the cruise, we want to make sure that there is a specific angle there. And during the cruise, we tilt the fuselage in a way that it can cause the least drag. So it can cause less fuel consumption and everything, better performance. So that is my understanding of instant angle, instead of saying that instant angle is for maximizing the takeoff lift. I think it's to reduce the drag for fuselage during the cruise. And the next one is slide 10 for the propulsion. And for this one, I think it'd be nicer if you can add what is the actual power that your snap engine can produce, or what is the thrust that you design the power plant can produce. And then we can compare the initial requirement and the actual design, right? To see, okay, my design satisfies my requirement, then my design is good, right? So I just feel that it'd be nicer you could put that, because when we talk about the wind design, when we talk about the propulsion, most important thing, we want to know what is the power it can produce, or what the thrust the power plant can produce, right? So that is for that part. And the next one is page 12. I was just wondering, it's not something wrong or a mistake or anything. I was just wondering why you use two different types of tanks. So one is bladder tanks and one is the rigid tanks.
I think our justification for that was the wings are more likely to get shot up. So yeah, the self-healing properties of the bladder tank would be used there.
Okay.
As well as because I'm sorry, go ahead.
Sorry, you go ahead.
So also because the wings can have sort of more awkward geometry, because you're storing the landing gear as well as you have the guns where the ammunition storage is. So you have an awkward geometry that just wouldn't really work with a rigid tank. And then if you did like a bladder inside of the fuselage, then you have a bladder which is malleable in basically a vertical area. So you'll have it start squishing on itself, like compressing on itself, which then you'll have more fuel getting accidentally, left out because you can't get to it.
Okay,
like unusable fuel.
Yes, thank you. Thank you for the clarification. Yeah, it really makes sense. So the next one is for the crew station and design. It's on page 18. So for the crew station design, I think the most important thing is the visibility. So it would be nicer if you can include the visibility of your designed crew station in this slide. It's like over the nose angle, side angle, and the angle like back to the tail to prove that, okay, my designed crew station satisfy all the visibility requirements. for the attack aircraft. And the next one is on page 22. So I see that the one sentence is like create a barrel to further crack propagation. I was wondering like how the structure can create a barrel for the crack propagation.
So I'm not sure if you want to get this one, Michael, but so how it works is what we learned in mechanics and material class, actually, as well as stability and control of aircraft, is that by making basically the skin as well as these bulkheads and riveting the skin onto it, you're effectively making a barrier for further crack propagation, because once it hits those rivets, it wants to break off at the rivet, but it doesn't want to keep propagating into the next section. So you, instead of having a whole section crack where it's going from, oh, the front of the fuselage all the way to the tail, you only have one little square break, in which case it's really easy to replace and won't cause complete structural failure if you're in flight, which is pretty important for military aircraft, because if you get shot, you have very high chance of getting a crack propagation at where you got hit. So it's really important that you have these bulkheads, these rivets, these stringers, because they're going to stop that from just propagating from one section to another to another.
And I can just add to that a little bit, kind of with the semi-monocoque structure. If you kind of look closely at the picture, you can see how the formers are going one way, and then the skin, or not the skin, the stringers are going like perpendicular to that. So having the stringers and then the actual formers connecting all of the stringers together, and then having all the different components, you have the stringers, which is like the foundation, the formers, which holds the foundation together, and then the skin and the bulkhead, which kind of creates a little casing around it. So all of these components together, when compared with the truss and monocoque structures, you can see how this seems like it would be more sturdy and more stable. And in our structures class, we also learned a lot about the semi-monocoque structure and how it's one of the most used in the field. So kind of went with that, and then based off of the different research we did, we determined that for our aircraft, this would be the best and help us be the most sturdy. And especially during combat, you want a lot of protection on your aircraft, especially in the fuselage, where you have a lot of the important components. So we determined that this one would be best suited for us and would be the strongest and most applicable here. Yeah,
I agree. So first, I agree that the fastener hole can sometimes function as the stop hole for the preparation. And also, I agree that, as we just said, the semi-monocoque is the best structure for the fuselage right now. So I agree with both of them. And for the specifically for the crack propagation, well, I have done my research on the crack propagation for my whole PhD years. So I would say it is true that a fastener hole, if you have fastener hole on the way of a crack propagation, it can function as stop hole, and then the crack propagation will stop there. But at the same time, we should be aware that the more fastener hole you have on the fuselage or the frame or the stringer, there's more initial crack generated, right? That is the source of the crack propagation. So, because when we drill a hole during the manufacturing or during the maintenance, when we drill a hole, the hole is not perfect. There's always some initial crack generated that is not, it cannot be avoided. And then we have a hole, we have initial crack, we have stress concentration. It will start the crack propagation. And also, when a crack causes a failure, it will not be so large that it's propagated from one frame to another frame or from one stringer to another stringer. It would, if it's that significant, your structure already failed already. So I would consider to be more careful on this kind of statement, create a barrel for further crack propagation. For what I said, I believe it makes sense, but if you consider from the other side, you are generating more initial crack and you have stress concentration around the hole anyway. So just want to be careful on that part. So the next one I was wondering is, it's not something like mistake or anything. I was just curious on page 27. So normally we have the horizontal tail and the elevator is like expand like almost the entire horizontal stabilizer. And now in your design is 30%. I was wondering like why?
I believe that's straight from the book.
Yeah, I think we chose that from the book. That was what was recommended. 30% of like the vertical tail cord for the rudder, and then 30% of the horizontal tail cord.
Okay, great. Thank you. I will double check on that. So, and
Do you mean like the trailing edge? Why is it from here to here instead of the whole trailing edge? Or do you mean from here to here to the cord?
oh, I think I read wrong. So the question I asked is it's not the cord percentage, is in the span-wise direction.
Oh, okay. From here to here.
Yeah. So right now, so yes, it's so your design is 50%, right?
Yes,
Yes.
for the elevators.
Yeah. So my question becomes: normally we consider it's like about 90%, and now your design is 50%. Sorry, I made a mistake before.
I think we also got that right from the book. I know we chose to do the inner versus the outer because if you do it for the part where it's thicker, it obviously has a larger effect than, say, the tip of the wing. But I believe that was from the book. I could be mistaken.
Okay, I will check on that later. For the slide page 31, so I can, from the center gravity envelope, I can see a very big change of the center gravity between from the start to takeoff. So I was wondering what causes a huge change, and also from landing to the very end.
I guess.
Are you referring to this horizontal line right here?
Yes, and the bottom horizontal line. So it's like
So the reason I actually included these horizontal lines this is actually a misunderstanding of what I'm trying to convey in this figure. I probably should have just deleted these lines to begin with. This is just so you could better read where the starting weight was, as well as the final weight after landing. That was the purpose of that one. If you look right here to the forward CG limit and the aft CG limit, it's actually a very small distance. I had some difficulty making this figure. I actually had to do it in PowerPoint because of just how the formulas happened. So I tried to make everything to scale using that method, and it actually just proved very difficult. So if we got rid of all the bombs and all the weight, you end up about right there, which this is the CG estimation with when you have all the weight and all the explosives at takeoff.
Oh, okay.
And then the aft CG limit is if you had basically no fuel, but all your ordnance. And the forward CG limit was if you had, I believe, all the fuel, but no ordnance.
Oh, okay. So
it was the max possible of, okay, where is this going to be with different combinations of things? And then to make sure that it was actually stable, we made sure that this forward CG and this aft CG fit within the base of these of the front wheel and the back wheel. Because if your center of gravity is outside the base of the wheel, then obviously you're going to tip. It's going to tip. So we spent the majority of it of our time to make sure that these forward CG limit and the aft CG limit never left the base, no matter what configuration you could possibly met for the aircraft.
Okay, great. Thank you for the clarification. Yeah, because I feel that when you put a line there, I thought it's like start from like takeoff and then like a climb, cruise, and landing is like you have the line so I think that is my understanding mistake. So it's basically is the range of the center of gravity of your aircraft during all situations. So the line doesn't represent from takeoff to landing. Okay, great. Thank you for your clarification.
Yeah, now I'll change that figure. Now that I know that, I didn't think it would be interpreted that way. I should delete that top line.
Yes, because in the textbook, it actually has a CG envelope start from like takeoff, taxi, takeoff, climb, and then cruise or loiter, and then descending and landing. And then they have the line connected, and it's represented the whole during one complete flight, how the center of gravity move during one flight. So it's like easily can make us feel that your line connecting here is also from takeoff to landing. So
it was actually quite amazing because the fuel, how we have it situated is so close to that starting point that the changes that you see are so small that it was almost like non-perceivable. So I had to define basically, okay, after how many points of the trip for the first mission is it finally noticeable? And I found it was like right after loiter, because you burn so much fuel during the loiter that you can finally see an actual change in the center of gravity. But then I was also thinking of, if we're doing the first mission and during that loiter, you're dropping explosives, and depending on which explosives you're dropping, how much weight you're losing. Oh, am I dropping only one side of explosives instead of like both wings? Am I unbalanced? How is this going to change the center of gravity? So that's why I focused more on, what is the possible, what's the most extreme I could possibly reach for the center of gravity? Because I don't know exactly what's going to happen during this flight. I know that we're taking off, I know we're cruising, I know we're loitering, but what's happening during the loiter? Am I dropping explosives? Am I getting shot at? Am I losing parts? Or stuff like that. So that's why I focused more on that.
Great. Thank you for your clarification. So the next one is also not a mistake or anything on page 34. So is this like accidentally is positive 0.138, negative 0.138, or is
that was actually completely by chance.
Because I was surprised. Wow, there's the same value, just different sign. So yeah, so if you set this calculated result, great. There's nothing wrong with that.
Once you hit like the 5th decimal, it started changing. But like the first 3, I was like, that's different. Didn't expect that.
Yeah, I feel like, why is that the same value? And so on page 36, so I see that the fuel use is about 1,000 pounds. So what is a designed fuel capacity for your aircraft?
I think it's actually like the total amount of fuel that we can use is like 4,000 pounds or something like that. Yeah.
I believe it's that high.
I think it is. Or no, I might be thinking of armament.
You're thinking of
armament.
I was
takes
thinking
up.
of these too. Yeah, I was thinking of armament.
The amount of fuel that we have on the plane was actually quite substantial, just because of how much fuel you're burning during that loiter. That 3 hours that you're in the air holding all that weight up, you burn just a substantial amount of fuel. So you just had a huge amount of fuel. That's why we ended up putting the fuel, we're going to put it in the wings. We're also going to put it in the fuselage, because we had to take up so much space to carry all this fuel for just that long duration sitting over the battlefield. And then having that excess fuel, so, if I miss the runway, I need to come back, or I'm damaged in flight or damaged in battle, and I'm either burning fuel at a higher rate than I typically would, or not getting the most efficiency out of my motor because there's a hole in it, stuff like that. So we actually had a substantial amount of weight, or substantial amount of fuel weight.
I believe it was actually around 3,000 pounds, if I remember correctly.
3,000.
Around there.
Yeah, we have it in the first slide, in the first 2, 3.
Was that the weight or the volume that we included when discussing propulsion? or fuel?
We actually might have included
No,
that.
for the propulsion, we had it in, we had the volume.
There
But
we go,
in
maximum,
the very first,
maximum fuel.
Oh,
yeah, we had it in pounds.
So let's say based on 1,000 pounds, let's forget about 3,000 first. 1,000 pounds, your endurance is already higher than requirement, right? And now you triple the fuel, so it means that, and also the range is much higher than, I don't remember.
I think this is unloaded as well. If it was carrying ordnance and, you know, at maximum cruise speed, it would use a lot more.
Yes, that's the case.
Yeah, this is right now, this is like unloaded, I think.
Oh,
Weight
okay.
final is the empty weight.
Okay, so it would be better to give the result of like design mission with actually 3,000 pounds of weapons on your aircraft, and then what is the range, what is endurance?
Okay, that's
Right.
good, because I was unsure about that.
Yeah,
So,
that's better than just say, okay, this is a range and endurance for a empty aircraft. Well, I want to know what is capability with all the payload on your aircraft.
okay, so for the range and endurance figures that we present, they should essentially be centered around the first design mission.
Design mission. Yeah,
Well,
yeah.
yeah, when you're carrying full payload and
Yes.
you know, just
Yes.
okay.
Yes, and if the, let's say, I would assume that it will be large, it'll be much, let's say, endurance will be smaller and range will be smaller, right? With the payload carried, and so you use the 3,000 pounds of fuel to calculate the endurance and range. If it's like several times higher than the requirements of our project, I would suggest that you can carry less fuel and the fuel tank can be smaller. And the weight of total aircraft can be smaller. So it's like an optimized optimization process, right? I know that there are some, you always want some margin for some unexpected situation, but in the product requirement, it's already give like, okay, reserve 45 minutes for lawyer or something. We already consider that. And if with 3,000 pounds of fuel, you calculate range and endurance is still several times higher than requirements, I would suggest you to reduce the fuel that your aircraft carry, and also reduce the volume of reduce the fuel tank weight volume. So to make your aircraft lighter actually can make your aircraft more competitive for this requirement, right?
Yeah, I think the values will look more reasonable once we scale them to the actual design mission.
Yeah, that's good. So I think that's all. So overall, really amazing job. I really like and enjoy your presentation, both the slides and the actual presentation today. And congratulations. Work hard on your final report.
Thank you.
Sounds good.